And otherwise, we'll keep going today. I think we can cover all of the next section, 3.5, because it's really just one proof, one long proof. And we'll probably need the whole class, so let's get going on this. So 3.4 was the place of parallels. We talked a little bit about theorems that are equivalent to Euclid's fifth postulate. This is now, we're coming back to this guy, the Saccheri. I usually call it the Saccheri-Legendre. My French isn't very good, so my pronunciation of his name is not the best, but the Saccheri-Legendre theorem. So you recall we have this guy Saccheri, this Italian priest, that really would have been the founder or father of non-Euclidean geometries had he been willing to accept his results and not just throw them away as absurd. So, and recall that he sort of did all this by trying to prove Euclid's fifth postulate as a theorem, right? So recall Saccheri was attempting to prove Euclid's fifth postulate as a theorem. So here's his idea. He's looking at a particular type of quadrilateral. His idea. He wants to study quadrilaterals with two congruent sides, with two sides that are congruent and perpendicular to a third side. So something like this. So you've got two sides that are congruent and perpendicular to a third side. Let's call it P, Q, R, and S. So this is what he has. Obviously, in the Euclidean realm, these two angles here, S and R, are going to be also right angles, yeah? But that's a strictly Euclidean result. The fact that these are right angles is a strictly Euclidean result. That's what he wants to prove. But what you can say in the neutral realm very easily is that they're at least congruent. Okay, so first, he shows that angle S must be congruent to angle R. And my first question to you, and I'll give you a few minutes to try and prove this, how does he do this? This is actually something we'll do sort of a lot of similar proofs like this in this class. So try and take a few minutes, try and think about how you would prove that angle S must be congruent to angle R.
just draw a line from Q to S or P to R?
Q to S or P to R. I've thought about that. That was actually my first attempt. But what do you do from there? Right, the problem is sort of if you draw on a diagonal, you're cutting this angle in half and somehow trying to compare it to this one.
So would be
not necessarily in half, but you're cutting it.
an equidistant point from S to P.
Equidistant point from S to P.
And then,
So you want to go halfway up here?
yeah, and then cut it to Q.
Yeah, so you're thinking along the right lines. The trick is actually to find the midpoint of this guy. Maybe I'll call it, we've already used P, we just call it X. Right, and draw on the perpendicular bisector. So draw on the perpendicular bisector to this line. It cuts through somewhere up here. I'm not going to claim this is halfway. It actually is, but just draw on this perpendicular bisector so that those are the same and these are right angles. It's a terrible right angle. And then we've got this quadrilateral congruence result, the only one we've stated, SAS, which is satisfied in this picture. So I'm not going to write this down. You can write down sort of whatever you want here. The textbook doesn't even include a proof of this, but the trick is, yeah, the easiest way to prove this is construct the perpendicular bisector to the line PQ. That gives you the fact that these are the same length and these angles are the same. Now we have S, A, S, A, S, A, S. By SAS, these are congruent, therefore these are actually the same length. That is exactly halfway between S and R. And these angles here must be congruent. So not a hard proof at all, but it does require SAS, or at least this method of proof requires SAS. So I'll very quickly sketch it. Draw a perpendicular bisector. Let's not say draw, but construct. Construct perpendicular bisector. For PQ, and then use SAS, AS. Okay, so he shows that they're congruent. Now there's three possibilities. Either these angles are less than 90 degrees, they're equal to 90 degrees, or they're bigger than 90 degrees. He's hoping he can rule out possibility 1 and 3 and show they must be equal to 90 degrees. So there are three possibilities. One is that measure of angle S equals measure of angle R is less than 90 degrees. I'll call it, we'll go the opposite order. Bigger than 90 degrees. 2, measure of angle S equals measure of angle R is equal to 90 degrees. And 3, measure of angle S equals measure of angle R is less than 90 degrees. And he gives these three things names. He says, okay, 1 would be the hypothesis of the obtuse angle. So, hypothesis of the obtuse angle. 2 would be the hypothesis of the right angle. And 3 would, of course, be the hypothesis of the acute angle. So he wants to prove Euclid's fifth postulate as a theorem by showing that 2 is true. In fact, only 2 is true. So he wants to rule out 1 and 3. But of course, in neutral geometry, which is what he's working in, if he doesn't have a parallel postulate, 2 and 3 are both possibilities. One is false, and he's able to disprove one. So that's what we're going to do today. So Saccheri is able to disprove one only. The hypothesis of the obtuse angle. Which is what we're going to do today, and it's going to follow as a corollary of a much more simple statement, or much more, I guess, friendly statement, much more intuitive statement. So the theorem is now the Saccheri-Legendre theorem. In fact, let's write this up here. Saccheri is able to disprove one only. It will be a corollary, an immediate corollary of the following theorem. And the Saccheri-Legendre theorem, in a nutshell, says that the angle sum of all triangles is less than or equal to 180 degrees. The angle sum of any triangle is less than or equal to 180 degrees. Which is a much nicer statement, right? Instead of looking at these strange Saccheri quadrilaterals and the statements about those, why not just make an equivalent statement about triangles? So this is the sort of equivalent triangle statement. The angle sum of any triangle is less than or equal to 180. We know in Euclidean it's of course always equal to 180, but this is neutral geometry, and you're allowed to be less. All right, so we'll spend the rest of the class proving this. I'm essentially going to invoke two lemmas that we haven't proven yet, and I'll prove them after. So let's get going here. So we're going to proceed by contradiction. Proceed by contradiction. Suppose there exists a triangle with angle sum larger than 180. And I'm going to phrase that in a slightly different way. So suppose there exists a triangle ABC with angle sum, instead of saying just straight up larger than 180, let's say it's 180 plus p, where p is some positive number, where p is bigger than 0. So the method of proof I'm going to invoke here is well, not necessarily a method, but a sort of style of writing proofs, is I'm going to make a claim. I'm going to say I claim the following is true, and then when we're done with the proof, I'm going to prove the claim. It's essentially invoking a lemma that I haven't proven yet. All right, so here's the first claim. We claim, this is claim number 1, because there will be 2 of these, that it is possible to produce another triangle. We'll call it triangle A1, B1, C1. So in my handwriting, those look like commas. Those are not commas, those are ones. A1, B1, C1. with the same angle sum. So with angle sum 180 degrees plus p, but with the measure of angle 1 less than or equal to 1/2 of the measure of angle A. Okay, so here's my first claim, is that I can produce another triangle with the same angle sum as the original, but where I'm shrinking the angle at one side. In fact, I'm shrinking it by a factor of 1/2, at least. All right, why am I doing this? Well, because then I can produce a sequence. So doing this again, we can build triangle A2, B2, C2 with angle sum 180 degrees plus P, but with measure of angle A2 less than or equal to 1/2 of the measure of angle A1, which of course is less than or equal to 1/4 of the measure of angle A. And if we do this as many times as we need, we can of course produce a triangle with the same angle sum as the original, but where one angle is as small as we want, right? So repeating this process, gives a sequence of triangles. Let's see, triangle ABC, triangle A1, B1, C1, triangle A2, B2, C2, and so on. Let's go to AN, BN, CN, where the angles at one side get smaller and smaller and smaller. Okay, a sequence of triangles with angle sum 180 degrees plus P, and with the measure of the angle AN less than or equal to 1/2 to the n times the measure of angle A. So I'm doing this because I want to make this angle sufficiently small. In particular, I want to make this angle less than P. All right, so let's choose n sufficiently large. Now, choose n sufficiently large so that the measure of angle AN is less than P. does that mean the other two angles in the triangle have to add up to? Remember, the three angles altogether, the angle sum is 180 plus p, right? If one angle is less than p, then the other two have to be bigger than 180, right? So, because the measure of angle AN plus the measure of angle BN plus the measure of angle CN is equal to 180 plus p, it follows that that measure of angle BN plus measure of angle CN is bigger than 180. And I'm going to claim that this is a contradiction. Right, so this is fairly obvious and fairly easy to do in Euclidean geometry, right? If I have a triangle, my goal here is I want to construct a triangle where one of the angles is really, 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 really small. So let's say this is just like 1 degree. And the total angle sum is, 100, maybe the total angle sum is 182 degrees. Don't write this down or anything. But if I can construct a triangle where one side is really, really small, and I'm saying I've got an angle sum bigger than 180, then those two angles together must be greater than 180, right? That's really easy to do in Euclidean geometry because you can just sort of stretch out your sides. I can sort of make this taller and taller and taller so that my angle becomes really, really small. And in Euclidean geometry, every triangle has 180 degrees, so of course the angle sum stays the same. But we're not in Euclidean geometry. In neutral geometry, not all triangles have the same angle sum, so there's no guarantee when I stretch this out to become a really, really small angle that the other angles sort of stay the same, right? So this is why we're having to go through this long process, and we're going to have to prove that we can do this, that this actually exists. But I'm building a sequence where my triangles have the same angle sum, but I am making one angle smaller and smaller and smaller. Okay? That's what we're doing here. And I make one angle sufficiently small so that if the total angle sum is bigger than 180, that means the two angles in particular must be bigger than 180. Do you understand this? Right, so that's what we're doing there. And yeah, my second claim is that this is a contradiction. So we claim, this is claim number 2 now, so second lemma essentially, that there does not exist a triangle with this property. Just to be clear, the property I'm talking about is this thing right here. The fact that two angles in particular sum up to something bigger than 180. So I'm not talking about the sequence of triangles anymore. And that's not hard to show, right? While it's hard to show that there can't be a triangle with total angle sum larger than 180, it is in fact fairly easy to show that two angles cannot sum to bigger than 180. This would just be the external angle theorem. Okay, so, and hence we have a contradiction. How do we get a contradiction? We got a contradiction by assuming that such a triangle existed, that a triangle with angle sum larger than 180 existed. So therefore P must be less than or equal to 0, or rather that the angle sum of any triangle ABC is less than or equal to 180 degrees. So I've opted to write the proof in this way to sort of give you a skeleton of what we're doing. This is why this works, but now we have to fill in two more details. These are these individual claims we made, right? Claim 1 and claim 2. But if we accept that they're true, then the proof is done. So proof of claim, we're going to go out of order here. We're going to do number 2 because it's the easier one. Proof of claim number 2. And again, this follows pretty much immediately from the external angle theorem, so let's see. Let's consider triangle PQR, and let X be a point so that P, then Q, then X are all collinear. So here's my triangle I'm looking at. P, Q, R. And let's see, so angle RQX. Angle RQX, that's an external angle. Or sorry, is an exterior angle. So the measure of angle RQX is bigger than the measure of angle, we'll go PRQ in particular here. So this is being an exterior angle, has to be bigger than the other opposite interior angles. Here I'm saying this guy is bigger, this angle is bigger than, which one are we looking at? PRQ, PRQ, this one. Is that the angle I want? Well, we'll see. So also I've got a pair of supplementary angles here. So also measure of angle PQR, it is the angle I want, plus the measure of angle RQX is equal to 180. All right, these two angles here are supplementary, so you add them together and they equal to 180. And here I should get my immediate result. Let's see. Hence, I want P RQ. Yeah. Hence, the measure of, the measure of angle PQR oh yeah, this is immediate, right? Measure of angle PQR plus measure of angle PRQ. These two angles sum to 180. This angle is bigger than this angle, right, by this line above. So if I substitute in PRQ instead of RQX, we get something less than 180. So we showed that for any given triangle, PQR, the sum of these two angles must be less than 180, right? Well, now you can do this for all pairs of angles. Take any of the three pairs that you want, and you can show they're always less than 180. So that establishes claim 2, that there doesn't exist a triangle with the property that just the sum of two angles is bigger than 180, right? Establishing claim number 2.
Wait, didn't you establish the two angles on like PRQ and PQR are less than 180, not QPR and PRQ are less than 180? Like the two angles on the right side of the triangle?
Did I do that? PQR, PRQ. Oops, yeah, sorry. Wrong. I've indicated the wrong angles here. All good though. Still, same thing, right? Sum of two interior angles cannot be bigger than 180. Is that right? Am I?
Sounds right.
Yeah. Okay, so just by the exterior angle theorem, that's all we need. It's pretty easy to show that two interior angles cannot sum to more than 180. And of course, the whole Saccheri-Legendre theorem says that three angles, in fact, can't sum to more than 180. So there's claim number 2. Now we have to come back to claim number 1, this claim that I can build a sequence of triangles where my angle sum doesn't change, but where I stretch out one angle to get smaller and smaller and smaller. I don't like calling my triangles P, Q, and R because I always lose track of, I find it much easier to think about ABC and different permutations of ABC and which angles are which, but P, Q, and R just confuses me. Anyway, proof of claim number 1. Proof of claim number 1. First we're going to do a construction we've already done in this class. And a construction you sort of repeat again for homework, so we should be pretty familiar with this. Consider triangle ABC, and let E be the midpoint of side BC. Let F be the point on the extended ray AE, so that A, then E, then F, and so that AE is the same length as EF. Okay, so we start off with this triangle ABC, we choose the midpoint of side BC, we construct this ray, and we choose F, so that F is the same distance from E as A is. We've done this construction once in class, and again you repeat it for homework, and of course the reason we're doing this is because these two triangles here are congruent, right? AEC and FEB. So we've done this construction before. And observed that triangle ABC is congruent to triangle FEB. that the right way around? Yes. All right, so these two sort of butterfly-shaped triangles are congruent to each other. Why? Well, it should be an immediate consequence of SAS, yeah. These are the same length, these are the same lengths, and those angles are the same. So immediately by SAS. What am I going to do here? What I'm going to do is I'm going to show that this triangle we started with, ABC, that triangle we started with, has the same angle sum as this new triangle I've built. In orange, ABF. Okay, so the angle sum of triangle ABC is equal to what? Well, let's give some of these angles names. How about I call this angle 1? I'm going to call this angle 1, angle 2, angle 3, and angle 4. So it's equal to the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4. And let's label some more angles in this picture, 5 and 6. I think that's all I'll need. So let's replace these with certain pieces. Still, I'm gonna call this measure of angle 1 and measure of angle 2. What does measure of angle 3 equal in this picture? It's congruent to another angle. By congruence of triangles. 3 is equal to 5, right? Those are the same angles. Measure of angle 5. And angle 4 is the same as angle 6. And again, notice that without this picture, without having drawn this picture, you would have no idea what these angles are, right? So if I didn't have that picture there, I would have to write down a precise description of what these are. So since I haven't done that, I will sort of note that you need to see the picture for this to make sense. And these follow because these guys are congruent to each other. Well, what is this second line? What's that the angle sum of? 1, 2, 5, and 6, that's the angle sum of the triangle ABF, right? Which equals angle sum of triangle ABF. That is triangle ABC and triangle ABF. Have the same angle sum. There's the first part of what I was trying to do. Right, what am I trying to do? I'm trying to build a triangle with the same angle sum as the original, but where I shrink down one angle every single time. Where I shrink angle A down by at least a factor of 1/2. And my claim is that this triangle will do. So I just need to show that one of these angles has been shrunk down by a factor of 1/2 at least. And so finally, note that measure of angle A is angle 1 plus angle 4. And if I replace this with a congruent angle, angle 4 is the same as which angle? Angle 6, right? Plus measure of angle 6. So the measure of angle A is the sum of those two. What does it mean if a number is equal to the sum of two other numbers? It means one of these has to be at least half as big, right? Or they could both be exactly half, but otherwise one is at least half as big. So that is measure of angle A is less than or equal to 1/2 of measure of angle 1, or measure of angle A is less than or equal to 1/2 of measure of angle 6. One of those two things has to be true, right? Because it's equal to the sum of both of those angles, angle 1 and angle 6. So at least one of them is less than 1/2 of the value. Less than or equal to 1/2 of the value. Do you believe that? Cool. So now we're done. And now we're done. I've constructed a triangle. With the same angle sum, and where I'm guaranteed that one of these two interior angles is less than or equal to 1/2 of this original angle A. So depending on which one is the smaller one, I'm just going to label my triangle differently. So finally, if measure of angle A is less than or equal to, yeah, we'll go with this, 1/2 of measure of angle 1, let A1 be A, B1 be F, we'll go with B, B1 be B, and let C1 be F. So if this is the angle that's getting shrunk, I'm just going to call my triangle, I'm going to call that A1, B1, and C1. And then we've built it. If it's the other case, if angle 6 is the smaller one, and if measure of angle A is less than or equal to 1/2 of the measure of angle 6, well, now I just need to relabel everything. I'm going to call this point A1, sorry. So let A1 be F, and then B1 can be B, and C1 can be A. And we'll go with that situation. Again, there's a lot needed here because this is not as easy as it is in Euclidean. In Euclidean, you're guaranteed that angle sums always stay the same, so you can just stretch out your triangles infinitely. In neutral geometry, there's no guarantee that when I look at a new triangle, when I sort of start stretching out a particular angle, that my angle sum stays the same. So this is why we have to go through this complicated construction here of, okay, I've built a congruent triangle with the same angle sum, or not congruent, but a triangle with the same angle sum, and now I have to look at which angle is getting shrunk. Is it this one or this one? And then sort of label my vertices accordingly to match up with the theorem. And then once you've done this once, you can do this infinitely many times, right? Now you can take this triangle, you can build a triangle with the same angle sum, and where this angle, or this one depending on how you label things, is getting shrunk again by a factor of 1/2. So we only have to do this once, and then we have the process done. So there's proof of the claim. Really, really, really big deal. All right, so this is a huge theorem, hence the fact that it has its name, the Saccheri-Legendre theorem, because it's a big deal, it's an important one. So yeah, this is as far as we can go with it, unfortunately. In neutral geometry, all triangles have angle sum less than or equal to 180. Once you impose parallel postulates, once you impose Playfair's or the Euclidean parallel postulate, then you have the fact that all triangles have an angle sum of 180. But once you impose some sort of hyperbolic parallel postulate, then you get the other result, that all triangles have angle sums strictly less than 180. So I promised that Saccheri stuff with his quadrilaterals would follow as an immediate corollary, but we're pretty much out of time. It wouldn't take but 5 minutes, but we're pretty much out of time, so we'll stop here and we'll finish that off on Monday. Again, I'll have your exams uploaded within 2 hours max, probably. And yeah, have a nice weekend.